Hello and welcome back to another episode of Effective JaRu, the series where we will read effective Java and see if we can port the patterns presented here to idiomatic Rust. Chapter 6 is all about enums and annotations, and I'm quite excited because that's truly interesting. I've just read the first part of it and realized that there's a lot of stuff that we have to port, so let's get going. So use enums instead of ints in constants. Of course, Rust people know that because enums are very powerful, and you would be surprised to see how differently they're implemented in Java and what this means for how they are used. That's quite amazing. So so there's just an example here with how much better enums are for certain types of things. I don't have to deal with that. But here, this one, enum type with data and behavior. So that's a planet. And we have a few different planets here. And you might wonder what this means. And, my Rust brain tried to understand what this might mean. Because in Rust, well, let's port it to Rust and then we will see what Rust means and not. Yeah, I don't know why this looks different here. I don't know who did that, so I have to fix it up real quick. Real quick means still too slow for my taste. So much in the way of the cursor when navigating. Yeah, anyway, here we go. That is that, and we are done. So let's have something like it in here, and I think I will start with we'll have a unit test right away. Tests, so st tests unit.rs, which forces me, it's more like it's an integration test technically, so I have to pull in the library itself, and can be sure that I can only use the exported stuff when I would be in the module here. Obviously, I could use everything that is defined in here, because things by default are package private in Rust, right? Or module private, you could say. So no tests for us, but we have a planet enum and shall see how that looks. So I will restrain myself to just a few of these, the interesting ones. So Earth. Yeah, I don't know why that is common. Idiomatic Rust definitely means you don't pretend these are constants, which is the first main difference. And an enum variant in Rust is not a constant, right? It carries no data, but it can carry data that is initialized in the moment you create that variant. Whereas an enum in Java is really like a set of constants, right? This is it. This is why it's capitalized here. It makes sense. This is why it's pre-initialized with data. That's kind of static final stuff here. And yeah, it's totally different. And we have to, I just now try to simulate that. I think, this can be misleading because in fact, this is, I don't know if an enum or an enum set here is the right representation for planets, right? Because planets, after all, are a thing that is, there are billions of that in the universe. And if you want to represent a planet, I don't think you would do it that way. Maybe you have a program that is very, very limited, but, to me, this seems like the wrong usage of enum in the first place. So kind of design failure. But maybe that is just supposed to be some sort of example and I just take it as it is. Okay, so I take it as it is. And yeah, if I wanted to specify data fields, I could do this. This is a unit variant, so it carries no data. And now I could say, well, I could have a tuple struct here. So we have, what is this, mass and radius. Whereas both are F64. F64. Oh, sorry. So in that case, it would be just unnamed. I could have a struct here, which would mean I have to name these fields. Mass and radius. There we go. This is all I can do here, but I cannot initialize these values because these things are not constants, right? Each variant here is created accordingly. And so we can't do it. If you wanted to attach constant data, we would now have to do some mapping, which is, fine with me. But it really shows that this stuff here, in Rust, these are not constants. It's just like that. And it's a good thing. If that's the design that people make up just because they think they have to use it that way, then I think better not. So I choose Earth and Mars, and I would like to have Pluto. Pluto, Mars, and radius. Maybe we can Google that real quick. Because Pluto has been quite active in the science industry. Pluto Wiki. I think the wiki will have this kind of information, huh? The planet. So interesting. Where's the mass? Here's the mass. Oh shit. How can I specify that? With E? I've never done that. Alright. Then I don't do that. Then I just use Saturn or Jupiter. There is a movie ascending Jupiter, so maybe this is why I chose this one. Okay, so here we have the enum declaration. It's really just a unit enum, and it carries no data at all. Interestingly, the way this is implemented in Java, each of these is a static final and I think public field of an instance of a planet, and this is why you can provide data here. This is really just going to the constructor that is package private right now. And then, the data can be accessed in this case through constructors, but of course, only because this is private final, right? You could also make this publicly accessible if you like. So yeah, you couldn't really use enums in Java the way you would do that. It's really like you would do it in Rust. It's really like a set of constants and nothing more. Okay, so let's implement the planet here to get the data associated with it. So we have a mass, pubfn mass, which returns an F64. Here we go, and this is why I chose to have a small switch here. I just want to match case, because if we match on this one, yeah, maybe I also import all of this, huh? Yeah, can I import this right here? Can I say, I think I can. So I want to have these individual fields and don't want to have to prefix the planet all the time. So I can use planet everything, right? This should work. So now I have Earth, and I map Earth to, so mass is the first field, Earth to this. I think it should be possible to specify values like this. Earth, Mars, and Jupiter, which shall be that. Yeah, that's a boring part, right? So the great thing is about the Rust matches that they have to be exhaustive, so you will never forget a field. This is something you read in the book all the time. If you use switches, then you can forget new variants that are added to the enumeration, which makes it unsafe. Then you have to work around that, which makes it more cumbersome and more convoluted and more difficult to understand. And this is what you have to do in Java, just because a match is not exhaustive. I mean, it's not a match technically, it's a switch that we don't even have in Rust. So anyway, that's what we do. No explicit return, as you can see. The return, every expression has a return statement, and the match in this case returns something in each branch. and it's always a double. I don't have to specify it even because type inference will make sure that this will be a double. Okay, so we have a mass. Then we have pop-event. I will just copy this then. Pop-event radius. The great thing is that right now all the data is static, right? There's no space taken on the stack for this. It's all just somewhere in the static area of the executable that we will produce. So now again, from the radius standpoint, Jupiter is this, Mars is this, and Earth is this. Thank you. Good. So I think the data we have attached, surface gravity, we can now compute. This is cached in this case because premature optimization, I'd say, that you shouldn't do. So if you can compute something, I say compute it and let the optimizer do its thing, right? In Rust, you would never have a field for this. I mean, I wouldn't know why. So it would definitely be premature optimization. So surface gravity is something that we can definitely compute. And considering that we have the data already in a match statement, now all we have to do is to actually compute it. So, oh, where's the G here? So it's this times self-mass by radius. So this is what I do. I don't want to make this call twice, even though I think that this will be optimized anyway. However, I think it's easier to read if it's shorter. So let's do it that way. Or radius square, because that is the radius square, right? By self radius pow 2 or something. Let's see, I have no idea. I would like to look it up real quick, because I think the F64 or generally floating point types, they have facilities to easily get the power of something. Here, pow I shall be sufficient. Oh no! Come on. Yeah, this is annoying. I don't need that feature to minimize a window. Never needed it, will never need it, would like to deactivate it. Anyway, here we go. Pow I. Semicolon here would basically mean that we return unit instead of an F64. Don't want to do that. Speaking of which, F64 is what we return. Alright. So that's the surface gravity. Then we have surface weight. Pop-fn surface weight, which takes a self, returns an F64. Oh yeah, and it takes a mass. And now it's just mass by self surface gravity. There we go. Cool. So that's our implementation. This is how it looks in Rust. Interestingly, still less stuff, still less code compared to Java. Which surprises me a bit. Okay, maybe it's because we only have 3 fields. If you would have all the fields here, it would be more. Let's see. Let's write the first test planet. And there's no code here, but I've seen in the book here it uses the planet, allowing you to compute the weight that you would have on a given planet. And unfortunately, I'm unable to specify I'm unable to specify arguments here. Damn it. And I don't know how to call this myself. I think I managed maybe once. Maybe I did. Java, and then you just specify the class search path, possibly. And yeah, the class path. I think this could be it, huh? Chapter 6, item 30. And then what? Then I have to specify the weight table. Yeah. Cool. So now we get something here. It's not even taking that long to execute that. I thought the Java startup time would be worse. But maybe they optimized something, or considering that we have nothing to load, it really notes nothing. That's good. Java doesn't have to be total shit. Did I say that? Yeah, I'm just used to these huge applications that take ages to do anything and feel kind of sluggish in the process. So yeah, so that's the values. We shall compare them with what we have. So on Earth, I weigh as much as I think I would weigh. On Mars, it's different. Yeah. So let's implement something that we can use for the test cases. Partial equality. Clone could be interesting, even though we probably will not need it. And debug. Debug is very interesting. Because right now we cannot convert into a string. We can print debug strings, but we cannot print anything else. And in the Java world, you automatically get a toString implementation that prints your class name. In Rust, you don't have anything unless you either automatically generate it or you implement it, right? So let me look it up real quick. Usually I implement, actually I don't need to look anything up. Usually I implement for this stuff impl as ref str for planet, because this means we can represent ourselves as a reference to a string, which is efficient because that way we don't allocate a string on the heap, which toString would do to us. So let's implement that real quick. We have fn as ref, taking a string. Sorry, we don't take a string, we take a planet, which, you know, this is our type here, and this is just the argument or the instance that we want. The type is kind of preset. That's the special case, the self-special case, so to speak, to remove any redundancy that this would have, and then return a string slice. And then it's really about matching on ourselves again and saying that for Earth return Earth, for Mars return Mars, for Jupiter return Jupiter. There we go. So now we can represent ourselves as string and should be close to being able to implement the weight table here. Planet weights. In a way, that's a program, right? So let's not put the unit test right here. Let's not implement it as unit test. Let's implement it as weight table. So we can easily do this by creating a new file, actually in bin. That's a bit, you know, the first time I used this, it's a bit of a special handling that Cargo does. So we can just drop our files there. Weight table. Now we have a main here. Pull in item 30. Use everything there. Item 30. Planet. And now we can start acting on this. So let's get the first argument, use std-env. And we shall parse it into a weight, right? So let weight be an f64. And we parse it from the first argument. So it's env args. Next, that's an iterator over strings. And then we can parse it. And this parsing will yield a result. And the problem is that, you know, we have to deal with that in some way. We can unwrap it, then parsing errors will cause a panic in the program. And sure, this could also fail, by the way. So now we can start the inline error handling. So next will yield an optional string. And we can say, well, unwrap it, but tell me, but I expect something, you know, unwrapping while printing a nice error message, basically. So expect first argument must be the earth weight in whatever unit, right? It doesn't really matter, actually. And then we parse this, and this could be something useful or not. And an unwrap here will basically just tell us that we couldn't parse it. We could map the error and just panic here, printing it. So couldn't parse number with error. Then we just drop the error here, and that should be it. So now we should have all the error handling that we'd need to do this to do this nicely. And what else? Now we compute. Yeah, that's the earth weight, mass. Okay, so let mass be the weight by earth dot. Yeah, I think considering this is a unit and this is an instance automatically, I believe, so no need to instantiate anything here. Also, yeah, I think this should be it. Let's see. Surface gravity. Like this. So here we have the mass. And now we iterate through the planets. For P in, well, you guessed it, we need to set it up. So we have Earth. So there's no values for this because that's not how Rust, you know, we don't iterate over constants or anything. And, you know, in Rust, this is just very different. It's really a fancy set of constructors under a single roof, basically. Because each of these, they kind of serve as constructors, if you think about it. And yeah, that's really it. So we have Earth, Mars, Jupiter, and unfortunately this is not exhaustive, right? So here, now that we take these out ourselves, we would have the problem that Rust can't help us anymore. So in case we add something, we would possibly miss a variant here. And I'm thinking how we can alleviate that. And the answer is not at all. No, I wouldn't know how. So all allowed values we cannot get. I wouldn't know how. So that's a possible downfall of this implementation over the Java one, because this will always be automatically all the variants that there are. Okay, so we print a little bit of stuff here, which is weight on is So wait on P, which is the planet. Maybe I just type it out. Is, and then we have planet surface weight of the mass. And that is that. So let's see how that works. Let's see if it compiles. Cargo builds. It attempted to build the weight table, that's good. Display is not implemented. Which is okay. It's true, we didn't implement that. But we implemented as ref. So as ref should automatically determine that a string is needed. And then we have a type mismatch, map error. True, it is still a result. But in the error case, we get a callback and can panic outright. And then we can safely unwrap basically, because we will know that we now know that we would panic with our error here, otherwise it works. Okay, so that actually built. Let's run it. So panic, couldn't parse number with error, invalid float literal. Oh yeah, sure. Try to use this as float literal. The first argument, of course, is the file name of the executable, right? So we skip the first one and then hit the next one, and now we should see what our error handling can do. First argument must be the earth weight. So the only ugliness here is that we kind of do everything in line. So we panic all the time, right? And this panic kind of leads to some extra print out here that you probably don't want. So in a real program, you wouldn't just panic, but you would, print your error and return in some way. We don't do that. So if I say run and provide a rate that is foo, then couldn't parse number with error, invalid float literal. Okay. So now 64. And look, beautiful. Weight on Earth is 64, 24.29. Where's the Java one? 24.29. Yeah, the computation is correct. And I think we can set up a precision here. Maybe that will be better for us. Yeah, that's a bit less terrible. Yeah, looks good. And this is the version in Rust. Note that we do full checking, basically, full checking of our arguments. Not the prettiest one, but it's clear what happens. And thanks to type inference, we can just parse this, and it knows that it's supposed to parse into an F64. Question would be whether we have to do this. Type inference is quite smart. Not this time. Okay, because it could see that later it's used in an F64 context. But it's not that great yet. But it's quite great. Don't get me wrong here. It's pretty awesome. Yeah, so that is that implementation. This is how that would look in Rust. And we barely touched the surface on enums in Rust. Even though kind of that's the deal already, right? This is how it would work. This is how you do it. It's very, very different from what enums are in Java, that's for sure. Yeah, so the next one, the payroll day, I think we do in another session. So thanks for watching and have a great day.